here. Thank you for your attention.
Thank you very much for your nice talk. So we have 14 minutes left, so it's time for questions and comments. Okay, so there is a question from Vladimir Birekas. Please.
Okay, hi. Good evening.
Hi.
And
Good evening.
I would just like to ask if it really is needed that the system should be overdamped in order to minimize entropy production.
So, indeed, so very honestly, I'm sorry, but I don't understand what is overdamped system. So, but so Takahiro suggested me
I
to
mean,
say it is better. Yeah,
in the start of your talk, you
yeah,
said
yeah. I
that
know, I know.
the
I
system,
say.
yeah.
Mm, Here,
And
yes. So,
Mhm.
yeah, you mean here? I say that this is overdamped Japan system. あれ
yeah. I mean,
うんうん
is it only overdamped Langevin systems that for which the entropy is minimized, or can it be minimized if the Langevin system is not necessarily overdamped?
Sorry, so honestly, what I need, so I need that if there is a probability measure and there is a flow, then flow always satisfies continuity equation. I need this condition.
Okay, I see. Thank you.
Thank you. Sorry, I can't reply properly. Sorry. But
Okay, so
Takahiro, is there some comment about such a things?
yes, yeah. The Benamo-Brenian formula is only valid for overdamped systems because we don't have the same expression of the entropy production like the square of the mean local velocity for underdamped case. So that's my understanding. But I think the difference overdamped and underdamped is a kind of a jargon in physics or stochastic thermodynamics. So maybe it's not very relevant to mathematics community, I think.
Sorry, thank you. Thank you for your help.
Okay, so there is a question by Injen Yang.
Yes, hi.
Hi.
Thank you for the nice lecture. I'm curious,
Thank
instead
you.
of having the constant level diffusion matrix, the Langevin system, what happened if you have like a space-dependent diffusion matrix, like a SDE? Like how does the geodesic change, and is that the case corresponding to the manifold case in the omega space?
Okay, so you mean that if omega is Riemannian manifold, what happen? Your question?
So if the diffusion matrix itself is space dependent, does that correspond to the Riemann manifold in omega? And how does the geodesic change in that situation?
So even if omega is Riemannian manifold, so there is a geodesics. And so, okay, so in how do I say? In Euclidean space, where I write down. In Euclidean space, okay. So local mean velocity. So okay, if the pair attain the minimum, then local mean velocity is generated by line segment on Euclidean space. And Riemannian manifold, the local mean velocity is generated by minimal geodesic on Riemannian manifold.
Right. So does the space-dependent diffusion matrix gives you the Riemannian metric
sorry,
for
okay.
the omega, or?
Okay, so also space evolve something, or space omega is fixed, or in your question, omega depends on t, you mean?
No. So sorry.
Okay.
So you start from assuming the noise, the diffusion matrix your noise matrix is actually identity matrix, right? I'm
Okay.
just curious if that that noise, that the Wiener process itself, if it's
Okay.
space dependent, does that correspond to the omega space being a Riemann space?
Yeah.
That's
Okay.
right. Okay.
Yeah. Okay. So indeed, so when we consider Wasserstein metric, we consider the Riemannian manifold and probability measure. Okay, some measure. And then we can consider the Wiener space, but even in Wiener space, we can have such a Wasserstein metric. And of course, for example, convexity or concavity is changed, but we have similar result.
Okay, thank you.
Thank you.
Sorry, I was muted. So, okay, so other questions or comments? So, okay, so I still have a question about the definition of the gradient in this slide.
Okay.
So the left-hand side gradient S equals something. Sorry, the
Maybe this.
yes, this slide. So yeah, S of P is a function of the probability distribution, and its gradient is a function of X. Is that true? I mean, so sorry, gradient is a map from.
No, so sorry.
Relative.
Gradient is okay. In this context, gradient of gradient of that one is a vector field on Euclidean space. So then we don't mind each x. This is independent of x, and we consider the gradient of that one is equal to vector field on Rn.
I see. So,
Of course, so here it is depend on x, but
okay,
vector
so
field itself.
yeah, the gradient here is not equivalent to the nabla of P.
So okay, so
its
maybe
grad is
so
not the
this
same as nabla, right?
this is gradient on Rn.
Yes, yeah, right.
Gradient. And here, this gradient is with respect to Wasserstein distance.
Yeah, right.
Different one.
So they are different.
Yes,
Okay.
different. Because the space is different. So this is the function on Rn, and this is a function on P. This is a different one.
Yeah.
Sorry, no, it's not good. Yeah, it's not good notation, sorry.
Yeah, I get it. Thank you. Yeah. So we still have 5 minutes. So other questions? So from the mathematical point of view, what is the significance of this gradient flow? So you showed that the Fokker-Planck equation or the heat equation can be written in the form of the gradient of something. So is that why is that very important in mathematics? I mean, what is the main mathematical structure behind it?
Yeah, because so I'm working on differential geometry, then for us, so fundamental notion is curvature. And curvature is like acceleration, then we need second derivative. And so if the function is smooth, then it is easy to have a second derivative. But if the function is not smooth, then usually we can't have derivative. Then, so if curvature can be defined smooth space, and there are many attempts that even if the space is not smooth, we'd like to estimate curvature from below or from upper. Then, so Otto and Strum and Rott, Bilan and Astrum, Conlenesse notice that if, okay, especially, they notice that if, okay, free energy or relative entropy, okay, Shannon entropy, okay, I change. Shannon entropy, second derivative of Shannon entropy along minimal geodesic is bounded from above by some k if and only if, okay, only if and only if the rich curvature of M is bounded below by k. So first they notice that using Shannon entropy, the curvature bound is described. And convexity, to have convexity, of course we can derive it, but without differential structure, we have the convexity. Then, using this formulation, we can estimate or we can extend the notion of lower rich curvature to non-smooth spaces. So this is the important point from differential geometry.
Yeah, I see.
So, okay, so roughly speaking, if we'd like to know the lower rich curvature, then heat equation tell us it. So heat equation, if the space is like sphere, then we have canonical probability. But if just Euclidean space, we don't have. So then the geometry and heat equation relate to each other. And especially the behaves gives the lower rich curvature. And this is figured out via optimal transport theory.
Okay, thank you very much. So
Thank
yeah,
you.
it's on time, but if there is another comments or questions, I will take another one. If not, okay, let's thank the speaker again. Thank you very
Thank you
much.
so much. Thank you for your attention. Thank you.
Okay, so we are going to the next talk.
Hello, can you hear me?
Hi. Yes.
Yeah.
Okay, so the next talk is an invited talk by Patrick Potts. The talk title is The Second Law of Thermodynamics, from macroscopic to stochastic thermodynamics, including information. Okay, please.
Thank you very much for the introduction. So yes, I will talk about the second law of thermodynamics, and I would like to take you through a journey starting from macroscopic thermodynamics and then moving on to stochastic thermodynamics, which holds at the nanoscale where fluctuations matter, and then also talk about the thermodynamics of measurement and feedback, where information plays an important role. And so thermodynamics really helps us to understand which processes are physically possible and which processes do not occur in nature. So when we look at the macro scale, then thermodynamics was a driving force in the Industrial Revolution, and it helped to further develop and refine devices such as the steam engine and also refrigerators, so really devices that changed our daily lives. And now we apply thermodynamics to nanoscale systems and quantum systems. And the hope is, of course, that thermodynamics will again act as a driving force to push forward these emerging nano and quantum technologies. And now one important aspect or ingredient for these new technologies is feedback control. So feedback control enables a lot of processes. For instance, it can cool down a nanoparticle close to the ground state at room temperature. It can be used for error correction of superconducting circuits or for autonomously controlling a mechanical oscillator using light. And so understanding the thermodynamics of measurement and feedback helps us to find out what the potential is of this technology and also where the limitations lie. Right. And so after this brief motivation, I would like to start with the laws of thermodynamics. The first and the second law, which are written here. So on top, the first law tells us that a change in energy in a system can be split into heat and work. And so this is a statement of energy conservation, and it prevents a perpetuum mobile of the first kind, which is a device that runs indefinitely without an external energy source. So here exemplified by a lamp that powers itself using a solar panel. The second law of thermodynamics introduces the concept of entropy production, which is the sum of a change of entropy in the system and a term that is associated to the environment, which is typically the heat divided by temperature. And the second law states that this quantity is non-negative, and it also prevents a perpetuum mobile, one of the second kind. An example of that would be a boat that uses heat from the water in order to move forwards. So this machine then has an external energy source. It's the heat from the water, but this energy source violates the second law of thermodynamics, and this can, of course, not work, right? So these laws, they work for average values, right? They work at the macro scale where fluctuations don't matter, and at the nanoscale, they still work for the averages of heat and work and entropy production. But what happens now when we go to fluctuating quantities and think of changes in energy, heat, work, and entropy in single experimental runs? Well, the first law is still true for classical systems because it's simply energy conservation, but already for quantum systems, things become a bit difficult. So there's a whole body of literature on how to even define work as a fluctuating quantity. And quite generally, one can say that it becomes difficult to write down such an equality, treating work, heat, and internal energy as fluctuating quantities in quantum systems due to the role of the observer. But today I don't want to go into this. Today I want to focus on the second law, which already for classical systems breaks down once we treat entropy production as a fluctuating quantity. So we may observe processes where entropy is reduced, right? Now, we can still make a lot of statements about this fluctuating entropy. In particular, there is the so-called fluctuation theorem, which is a generalization of the second law to fluctuating systems. And to understand the fluctuation theorem, we can look at a random particle, a particle kind of moving in a random way, and it could follow this trajectory illustrated in red here. This trajectory we call x, but since the particle is stochastic, we may also observe it doing the backward path of this trajectory, so kind of following the red line in the reverse order, and that we call the time reverse trajectory, xtr. Along a trajectory, entropy will be produced, and the entropy production produced along this trajectory we denote by sigma of x. And then the fluctuation theorem tells us that the probability of observing a trajectory is related to the probability of observing the time-reversed trajectory, and this ratio is exponentially suppressed in entropy. And from this we can learn quite a bit. For instance, we can try to apply to macroscopic scenarios or processes like a glass shattering. So if we have a glass shattering, we have of the order of 10 to the 23 particles involved in this process, and so the entropy production will be on this order times the Boltzmann constant. So this is a huge number. And then, of course, this exponential on the right-hand side will simply be 0. And that means that we will never observe.
Sorry, Takahiro, everyone, can you see slides? Because I can't see slides.
I can see the slide.
I can see the slides, yeah.
Okay. Yeah, sorry. Okay. I'm glad that at least some of the people can see the slides. They're kind of important for the talk. Right. So with such a large entropy production, then of course this ratio here is simply 0, and we can conclude that we can only observe the processes where entropy production is positive. And yeah, so for macroscopic systems, we do get the second law of thermodynamics without having to worry about the average of the entropy production. But this is no longer true when we go to the nanoscale, because there maybe a single degree of freedom is involved in a process and the entropy production becomes small. And then we may very well observe processes where entropy is reduced. From this fluctuation theorem, we can then derive a so-called integral fluctuation theorem, which tells us that the average of this quantity is equal to 1. And from this, on the other hand, we can then derive, using Jensen's inequality, the second law for the average entropy production. And so this shows that the fluctuation theorem is a proper generalization of the second law, because it does include the second law for the average value, but it tells us more. It also tells us how entropy production is constrained as a fluctuating quantity. Now, before we can move on to feedback-controlled systems, I have to introduce one more ingredient, and this is the breaking of time reversal symmetry. So to this end, imagine an experiment where you change some control parameter in time. Could, for instance, be a voltage that is ramped up linearly. And then we call this experiment the forward experiment. Now, we consider also a so-called backward experiment where we time reverse this control parameter. So when it's increased linearly in time in the forward experiment, then in the backward experiment, it will be reduced linearly in time. And in this case, the fluctuation theorem relates the probability of a trajectory x to the probability of the time reversed trajectory in the backward experiment, which is the time reversed experiment, so to speak. And this ratio is still exponentially suppressed in entropy production. So importantly, we have different experiments in the numerator and in the denominator now of the fluctuation theorem. Right. And so with this, we have everything we need to go to feedback-controlled systems. For concreteness, I will focus on the example of Szilard's engine, which is illustrated here, which is an engine that uses a single particle in order to extract heat from an environment and turn it into work. And this works as follows. So we start with a single particle in a box, and then we introduce a partition in the middle, and then comes a very important step. Then we measure where the particle is. Here we find it on the right-hand side. So then we attach a weight to the right-hand side of the partition, and we're going to use the pressure exerted by the particle on this partition to lift the weight. And so in this step, work is extracted from the particle because the energy of the particle is reduced, and we're lifting the weight. After that, we remove the partition and the weight, and we let the particle re-equilibrate. And so in that step, heat is absorbed from the environment because the energy that is lost during the work extraction step has to be recovered to complete the cycle. And in a full cycle, we then extracted work, and this work is replaced by heat coming from the environment. So we turned heat from an equilibrium environment into work, and this is supposed to not be possible due to the second law of thermodynamics. But of course, here we do have access to microscopic degrees of freedom. We have information on microscopic degrees of freedom, and that changes the game. And so now we can ask, how can we extend the second law of thermodynamics to these scenarios? And one way of doing it is to appreciate that, well, in these feedback-controlled systems, fluctuations play a crucial role, right? In this measurement step, we don't know if the particle is left or right, and that's a random variable. And so if there wouldn't be any fluctuations, then we wouldn't get any information from the measurement either. And so appreciating that fluctuations are important, we can again start with the fluctuation theorem and try to generalize that to feedback-controlled systems. So here on the left is again the scenario without feedback, and I introduced one more symbol here, which I call the protocol lambda. So this protocol encodes all the parameters that we maybe change over time, all the control parameters. And without feedback, we just choose a fixed protocol in the forward experiment. And in the backward experiment, we then simply time reverse all control parameters. So we time reverse the protocol. Now, when we have feedback, that means that we no longer have just one protocol, but we are dealing now with a family of protocols. For each measurement outcome, we may apply a different protocol. So lambda is now lambda of y, where y denotes the measurement outcome. And now the tricky part is to define the backward experiment, because you can't simply time reverse measurement and feedback. Measurement comes before feedback, right? And the first backward experiment in the literature that I'm aware of goes back to Sagawa and Ueda, so the chair of this session actually. And in this backward experiment, one takes one member of this family of protocols and time reverses it and then applies it. No measurement, no feedback. Simply taking one of the forward protocols, time reversing it and applying it and going with it. And so this backward experiment results in the fluctuation theorem shown here on the right, where in addition to the entropy production, there's an information term appearing here. And when you take the average of this term, then you get the mutual information between the system state and the measurement outcome. And when we now do the same steps that result in the second law for the average without feedback, then we find that now the average entropy production is bounded by minus the mutual information. And I call this here outsmarting the second law because it tells us that if we have information on microscopic degrees of freedom, we can achieve negative entropy production even on average. Right? And now it turns out that this backward experiment here is not the only backward experiment that you can define. You can actually define many different backward experiments, and we came up with one that we find particularly useful. It is quite similar actually to the one here on the right. We also pick one member of the forward protocols, time reverse it, and simply apply it. But then we do perform measurements on the backward experiment, and we perform a post-selection at the end. And this gives rise in a different fluctuation theorem, where the information term here is not related to the mutual information, but to the so-called coarse-grained entropy production. And this coarse-grained entropy production, you can think of it as the entropy production that you can infer only from the measurement outcome. And this is now very useful because it tells you that this bound on the right-hand side, you get it from the measurement outcome. And this is typically what you have access to in a measurement. You have access to the measurement outcomes. And this is in contrast to the mutual information, where to evaluate it, you need to know the measurement outcome as well as the true underlying system state. Right. Okay, so now I would like to show you how these fluctuation theorems, they can actually be verified experimentally. And to this end, I will look at an experiment from the group of Villemeisi, which is based on quantum dots in a nanowire, as illustrated on the top left. And the colored areas here, they correspond to quantum dots. So the blue area is a quantum dot where an electron can jump on and off from this contact here. And in order to perform a Szilard experiment, we then need to measure the occupation of this dot. And this is being done with the right-hand side here. So when we drive a current through the purple dot, we can measure the current and we get this blue curve here. And we see it jumps between two values. And these two values correspond to the occupation of the blue dot, right? So by measuring the current here, we can measure the occupation of the blue dot. Now we can perform a Szilard type protocol where we start with the energy of the quantum dot somewhere here. And then we measure the occupation. Here we see it's empty and is equal to 0. Then we lift the energy of the quantum dot and then we slowly move it back down. While it moves back down, electrons can be exchanged with the environment, and that happens at the dashed lines. And when the quantum dot is full and we're moving the level down, then we're lowering the energy of the system, and that means we're extracting work. And that is illustrated in the upper green curve, where we see that the work is increased whenever the dot is full and the energy level is lowered. On the bottom, you see the entropy production, and you see essentially that entropy is produced whenever an electron jumps on or off the quantum dot. Right? Now one can make many experiments and come up with and make this histogram here on the top, which shows you a histogram of the extracted work. In order to verify the fluctuation theorem, one also needs to make histograms for the backward experiments. So these are the two other histograms for the two backward experiments I illustrated. And in these backward experiments, as I mentioned, we have to kind of flip the protocol. So in these backward experiments, the level is raised very slowly and then quickly reduced. Right, and now with these histograms, one can kind of check the fluctuation theorems. So this is illustrated in these two panels for the two different fluctuation theorems. The data should lie on this straight line, and we see that kind of within the error bars, roughly, this works. Of course, it doesn't work at the edges, but actually these are rare events where we simply don't have enough data to make really a strong statement. Right. Okay, so this was all for classical systems. Now we can move on to quantum systems, where we have some challenges. Right, so for quantum systems, for instance, there are no well-defined phase-space trajectories, and also measurements in general introduce backaction and the collapse of the wave function. And for these reasons, a fluctuation theorem that is applicable to continuous feedback in the quantum regime has been lacking for a long time. This gap has been filled by the group of Takahiro Sagawa a few years back with this very nice contribution to the field. But while this constitutes an important step forward, there are some shortcomings of this fluctuation theorem here. For instance, the information term is not accessible from measurements alone, similar to the mutual information, where you need the exact system state to actually evaluate it. The information term here also diverges when you go to the limit for strong and continuous measurements, which is a limit that we might want to consider. And the derivation is restricted to Lindblad dynamics, and while this is a very strong and important workhorse, sometimes we want to consider strong coupling where Lindblad dynamics breaks down. And so with a PhD student in my group, Casper Prech, we were able to come up with a fluctuation theorem that overcomes these shortcomings, essentially by considering unitary time evolution of system and environment interrupted by measurements at discrete times. So we consider a system state tensor with a thermal bath state, and then this is time evolved with a total Hamiltonian that includes Hamiltonian of a system, Hamiltonian of a bath, and coupling Hamiltonian. And then at discrete times, we make measurements which are described by Krauss operators, and the measurement outcomes are these y's. And of course, the Hamiltonian has to depend on the measurement outcomes to accommodate for feedback. Now, to define a fluctuation theorem, we have to define trajectories. And our trajectories here importantly have two parts. The first part is the set of all measurement outcomes. And the second part describes the trajectories of the system. So A here describes the initial state, F the final state of the system, and the E's describe energy eigenstates of the environment. And so a trajectory takes us from an eigenstate of the system, an energy eigenstate of the bath, then we make a bunch of measurements and get these outcomes, and then we get a final state and a final energy of the bath, right? Now we also have to define a backward experiment. And so in the backward experiment, we're again going to perform measurements. So these measurements have to be time reversed. Theta here is a time reversal operator. And also the control protocol has to be time reversed like that. And we're again going to apply a fixed protocol with measurements and post-selection, but no feedback. And then we get